So the next couple of lectures, what we're going to do is go through all the different parts of the SN2, and we're going to pretend that only that kind of substitution is available. For the next couple of lectures, at least, we'll ignore the fact that eliminations could occur and the fact that there are multiple substitution, well, actually, I guess just two substitution mechanisms. We're going to, like I said, just pretend there's only the SN2, and we're going to look at all of the individual parts. Once we feel really good about recognizing when an SN2 is going to occur, that's going to give us insight into when some of the other reactions will occur. So let's remind ourselves what different parts are required for an SN2. Keep in mind that nucleophile is probably the most important factor that we're going to look at to determine whether an SN2 happens. So we'll look at that specifically, but let's remind ourselves about the different parts that have to come together. And I'll draw this in just kind of a general way. So what we know of the SN2 reaction is that we need some sort of nucleophile that has a lone pair of electrons. And that is almost always the case. Like, you need some sort of source of electron density for that arrow to reach out with. The next thing that we're going to need is we're going to need, I'll abbreviate it as like in kind of an odd way with the electrophile and the leaving group. Remember, this whole entire thing, this is what we called a substrate. So we will be seeing a variety of substrates today, and I'll try to just kind of use one type of leaving group, but really we'll hold off on this for a future video lecture to kind of focus on that. Like I said, we're going to be focusing on the nucleophile. So these just highlighted in red, these are the different items that we'll eventually be addressing. And there's one other thing, which is solvent, but let's leave that alone for just now. So remind yourself that the way that these things react is that the nucleophile reaches out in an SN2 reaction, attacks the back side of that carbon, and then pops open this bond so that that leaving group does what a leaving group does. Leave. Pretty brilliant, right? So let's focus in on what makes a good nucleophile. One guiding principle in deciding whether something's a good nucleophile, it's a good idea to kind of keep your eye out for a negative charge. That's not to say that everything with a negative charge is automatically a good nucleophile, but just to start off this crazy discussion somewhere. That's kind of what I always look at to begin with. And it wouldn't be a chemistry class if there wasn't an exception to this. So it turns out that the best nucleophiles have a negative charge, and I'm already going to amend this and say, or are a nitrogen. And technically I should say anything in the pnictogen family, right? Nitrogen, phosphorus, things like that. They tend to be pretty good nucleophiles without even having a minus charge. And that just has to do with their kind of inborn reactivity. And obviously, if you have a nitrogen with a negative charge, holy crap, that's going to be a good nucleophile, or a phosphorus with a negative charge, or something like that. So that's really the first question that even when the world gets crazy and we have all these different competing reactions going on, this is really going to be the very first question that we have to answer. So what are some really good, let's just pick one, right? A good nucleophile with a negative charge. Probably the classic, or some things that we've already seen in previous videos. One from last term, for instance, would be our old friend, the acetylide, right? This is a methyl acetylide. So it turns out that that minus charge on that carbon right there really makes this thing want to reach out and attack carbons, electrophilic carbons. Keep in mind, though, that the thing that makes chemistry sometimes tough is that it's not always written in the same way. Obviously, like, it could be anything. It doesn't have a CH3 group on there. So it might be written with like something that looks like this. Right, and this is kind of the real substance that you would add to the reaction. Or like sometimes things can get a little tricky where they'll start off with the proton here, and then you'll treat it with a base. but really what they're trying to do is have you recognize that this is a nucleophile. And we'll see that when we start to see some real reactions going on here. So another really good nucleophile, one that's just like classic on the American Chemical Society exam for asking about SN2 reactions, is this nitrile. Right? Not surprisingly, it looks just like acetylide. Turns out that this thing is spectacular for a bunch of reasons in doing SN2 reactions. Other things with minus charges that are great nucleophiles. In just a second, I'll give you kind of a list of relative reactivities that kind of give you a good sense of like what the best nucleophiles are. Things like amides, right? Those are, if the best nucleophiles have a negative charge or a neutrally charged nitrogen, if that neutrally charged nitrogen is in fact a negative, those things tend to be really spectacular nucleophiles. So, apart from just memorizing a huge list of negatively charged species, it would probably be a little helpful to just kind of develop a couple of just like general assessment techniques for when something is a good nucleophile. I should have been an artist. Look how good this periodic table is. So one of the really common questions that you'll have to answer, let's say on an American Chemical Society exam or something for me, it'll have you rank nucleophiles, and this is something we'll do on a future homework. In general, all things being equal, as you go down a family, usually you have a stronger and stronger nucleophile. So let's write that down, right? Oh, and by the way, in terms of nucleophilicity, right, we're always on this, that division between metals and nonmetals. Like the nonmetals are always going to be your nucleophiles up here. But one thing that is always true is that as you go down that table, the NU strength increases. So, for instance, if you were looking at something in the same family, like let's say OH minus, which by the way is a spectacular nucleophile, versus SH minus. The fact that we are deeper in the same family for sulfur is going to make this guy be a much better nucleophile than OH minus. But again, like that's a relative rate kind of question. Like both of these are great nucleophiles. And so that's kind of something that I use as a way to understand that. If you're ever asked to explain the reasons for that, that's where things get a little funkier. And that has to do with the size of these different atoms. If you remember that atomic size increases as you go down the table, what we're saying with this SH being a stronger nucleophile, it's almost, I always thought about it as like a balloon animal, right? So if we had like a big giant sulfur with its minus charge, we can kind of squeeze that thing together like a balloon animal and kind of force that minus charge to be a little bit better of like a point charge. And approach the backside of carbons, whereas oxygen's this little tiny thing with a minus charge that you can't get that same kind of like directionality with. That's called the polarizability argument, and it's something you see here and there, and we'll definitely use it on occasion. But it turns out that if you just memorize that, that's probably gets you out of your difficulty. The other thing which we could compare, instead of comparing things in the same family, is we could compare some things in the same period, right? And so we'll go this way, right to left across a period. In this direction, the nucleophilic strength increases. All right? So in other words, if we're working across this thing where we've got a fluorine, an oxygen, a nitrogen, and a carbon, if you imagine each of those species with a negative charge, just to make sure that everything is equal, you're going to see that each one of these things becomes a better and better nucleophile as we go right to left across the table. I should mention, of course, that they have to have a lone pair of electrons available. So in other words, like if you had any kind of carbon, if that carbon didn't have a lone pair of electrons, it's not going to be a good nucleophile, right? And so that's kind of the qualifier in that statement right there. So, you know, an O minus, or sorry, OH minus is a little bit better than an F minus. An NH2 minus or an NR2 minus, that's definitely a better nucleophile than an OH minus. You get kind of the picture. So just a typical situation here is to see something like this where you have to pick out which one is the stronger nucleophile. What I'm saying is that this will be the carbanion will be the slightly stronger nucleophile. By the way, there's kind of some other issues with this that we'll talk about in terms of its basicity, which probably we'll talk about in the next slide here, or this next discussion. These aren't slides. But that is basically that thing, you know, these two things, really strong nucleophiles, and an SN2 reaction is going to happen. But the problem with this guy is that its reactivity is so crazy high that it actually does some other chemistry too. And so like keep in mind that all of these things that I'm talking about, like I'm trying to make the world a nice simple place where only one thing happens and we'll build in the rest of this stuff. No chemistry discussion would be complete without an obnoxious exception to a rule. The good news is that even though that this is probably important that you know now, it's going to become less and less important as you kind of go through the rest of your careers. So unfortunately, there's an obnoxious exception to this whole idea of the strongest nucleophiles being deeper in the table, right? Everything that we're about to talk about will become a little bit more clear when we get to acid-base chemistry, but it's not going to be until third term. So what we're going to do instead is just kind of memorize. You're going to hear the words coming out of my mouth, and if you hear me now and understand me later, as Arnold would say. And that is that as you go down the list in down the list in the halogen family specifically, your solvent matters, right? And this is something we'll talk about in a not so distant lecture video, the role of solvent. But it turns out that we kind of have to talk about it now in terms of nucleophilicity. And so it turns out that in a polar protic solvent, right? Like methanol, like water, like things that have kind of a heteroatom attached to an H, right? It turns out that trend is perfectly understandable in terms of what we've already talked about, right? I minus is going to be a little bit better than, oh my God, what is it? Br minus, which is a little better than Cl minus, which is a little better than F minus. Well, it turns out that even though that is the case and that, kind of follows the path of all the other things that we've been talking about in terms of the periodic table, it turns out if you are in a polar aprotic solvent, which by the way does happen quite often in organic chemistry, the trend completely reverses, right? And like I said, the reasons for this have to do with hydrogen bonding. If you're really interested in it, we'll talk about it, but just accept it for now. The problem is that we haven't really talked about the role of solvents just yet, so this is a little bit funky. I just wanted you to make sure that if you're going to write this on a note card or something like that, that you make a different note card for these two. Recognize that sometimes the ACS exam will get a little bit tricky. So polar protic solvents, we'll say like for our examples will be like water, methanol, etc., etc. We'll learn a whole bunch of polar aprotic solvents in that coming lecture here, but things like that are DMSO, DMF, acetone, all just, like I said, we'll talk about it. But the kind of funny thing happens in terms of nucleophilicity where fluorine ends up being a little bit better of a nucleophile here. And And really the reasons for that have to do with the fact that F- can hydrogen bond, right? And so if you imagine an F- in a solvent like this, right, you're going to have this huge solvation sphere of all kinds of solvents that are kind of like carried along for the ride, and you're not going to get that punch that you'd otherwise get. If you understand it, awesome. If not, don't worry about it. Just memorize it. So let's talk about another couple of issues with the nucleophilicity of something. And one of those issues that we should probably talk about, I guess we've already talked about it really, but if you need to take a look at, let's say, this thing, water versus hydroxide, keep in mind that like something with a minus charge, right, that's going to definitely be a better nucleophile than something like this. It's not to say that this cannot act as a nucleophile. It's just its rate's going to be really, really, really low. And in this world of complication, when one rate for a reaction becomes really low, usually that opens the door for some other crazy stuff happening. And we'll definitely talk more about the types of reactions that this guy does when we get into E1 and SN1 type reactions. So let's set up one more competition that'll allow us to talk a little bit about another factor that we should consider. You'll notice that like both of these are oxygens with a minus charge. And so you might think, oh, they're both spectacular nucleophiles. It turns out that this guy is a far better nucleophile than something like this. And the reason is, once again, the resonance, right? This guy right here has resonance, whereas this does not. And what you want in a nucleophile is you want that minus charge to just be on one place and ready to just punch the crap out of that other carbon at the end of the arrow. And so what I'm saying here is that the fact that we can do a resonance form where we take this oxygen and do that kind of push of arrows, and as a result end up with a species that looks like this in a resonance form. What that is really telling us is that, again, with resonance, we're not saying that it spends half of the time like this and half of the time like this, that the true picture of this thing is somewhere in the middle. So really, when we're looking at this, really it's only a half of a minus charge, if you want to think about it like that, right? That minus charge is kind of smeared over that entire thing. Like, so sometimes you'll even see books and such that instead of drawing resonance, we'll do this kind of crazy thing where they show kind of the partial bonds here and the fact that those minuses are kind of spread out like that. It turns out the act of doing that really does make this thing not good, not the best nucleophile. The last nucleophile topic that we need to talk about here is kind of a thorn in our sides a little bit for now. But keep in mind, good nucleophiles are often good bases. And that is like a really general statement, right? So let's actually see a case where, let's say that something is maybe not a good nucleophile that is a good base. Something like this, right? We could take a hydroxide with its minus charge. And then we could compare the nucleophilicity of that to something like methoxide with its minus charge. And then we could compare that to yet another species. Let's really go to the end of the earth here. This thing is called tert butoxide, right? And so each one of these you would look at, it would be an oxygen, which is pretty, nucleophilic. It's got a minus charge. Oh man, that's really nucleophilic. But there's a little bit of a problem if you think about what's actually happening in three-dimensional space with this guy, the tert butoxide, right? Keep in mind, in an SN2 reaction, what you're trying to do is you're trying to reach into this kind of, tough to access, backside of a carbon. God, that sounds awful. I'm sorry for those hand motions. I'm not editing that though. So this guy, when it tries to reach in and attack the substrate, what's going to happen is that there's going to be a steric hindrance way out here, right? And so steric hindrance just means junk in the trunk, like huge amounts of like crap that you kind of carry along with you. So it would be kind of like the, here's a horrible Sean analogy, right? Like imagine that I was like gonna punch a guy because I'm like super aggressive, right? And I would really want my fist to be pretty unencumbered, right? Well, if you put a bunch of like, beach balls and frilly lace around my hand, I'm gonna just, right? I'm not gonna be able to like really get a good punch. So that's kind of the way that I, in my chaotic COVID brain, understand what's going on with some of these nucleophilicity. So what the hell does that have to do with good nucleophiles, often good bases? Well, that guy is a great nucleophile and a darn good base. This guy is a great nucleophile and a darn good base. This guy is a pretty bad nucleophile, but a really heck of a base. Right? And what that's going to open the door for is the elimination side of the process that we're not allowed to think about just yet. So keep that kind of thing in mind too as we start to develop some of these rules. One thing that always helped me in my learning is some like concrete data, like go figure, we're chemists or scientists, right? We should probably use some data. So I found this table that'll hopefully be helpful to you. There you'll kind of see what's called the relative reactivity, right? So basically, as you look at the thing that's hopefully appeared there, the things towards the bottom with the really, really high relative rates, right? They've kept everything else the same. All the other parts are the same. They've just, just changed the nucleophile in this list. And you'll notice that thing at the bottom has a huge rate compared to something way up at the top, right? And I can't remember my table well enough, but I think water was the top relative rate of 1. Yeah, and that kind of gives you a recognition of the scale of something, right? What effect does putting a CH3 group on there have? And what effect does having a minus charge on there have? So you'll be able to kind of refer back to this hopefully in terms of like solidifying some of your understanding. I'll be back at you in a future video, and we'll talk about the substrate and leaving group effects of these reactions.